Okay, so welcome back, and this time we're going to talk about the equilibrium constant as it relates to cell potential. So, a couple things we need to be aware of. This is going to be a variation of the Nernst equation, and in particular it's going to be a variation of what I was referring to as the adjusted Nernst equation, which means the equation E is equal to standard cell potential minus 0.0591 over n times the log of q. And so what we're going to see in these cases where we're going to solve for k is to be k means that it has to be equilibrium, which means that the value for the cell potential of the cell, not the standard cell potential, but the cell potential of the cell has to be 0. So essentially it comes down to this statement. This then gives us an opportunity to rearrange this equation in order to derive it, but immediately upon E equaling 0, the Q instead becomes K. And so that is then how we end up at this equation, which works nicely at 25 degrees Celsius. If we want to adjust the temperature range at which we're looking, then we would have to deal with the original Nernst equation. E is equal to E naught minus RT over N times F natural log of Q. And so we'd have to go through an adjustment based on this equation. So not a huge deal, but a lot of the times we're going to see that the temperature that they're looking at is 25 degrees Celsius. And so if this were the case, it would have been instead natural log of K is equal to NF E naught over RT. And so if we're going to use this equation that I've got circled right here, we're going to put it to use on a question like, what is the K value for the reaction associated with a cell comprised of cobalt and manganese electrodes? And so that puts us in a position now of twofold. We need to take a look and see what our standard cell potential is going to be. So we've got this, and we're going to write those half reactions like I was saying. And so with cobalt, we've got CO2 plus 2 electrons goes to cobalt solid. And in the case of manganese, we've got Mn2 plus 2 electrons goes to manganese solid. We've got standard cell potentials for these two, in the case of cobalt being negative 0.28 volts, and in the case of manganese being negative 1.18 volts. And so, as we're dealing with this, one of these two is going to have to be flipped. We tend to want to flip the more negative of the two equations, which means that we're going to flip the manganese equation, giving us this instead. And thankfully, as we look at this, we've got our electrons balanced out, which is nice because that's going to establish, as we've talked about in other videos, our N value, the number of moles of electrons. And in terms of our standard cell potential, we are looking at a value of 0.90 volts. So we've got a lot of the information that we're going to need in order to be able to put our work together. So what we can do now is start working with the equation. So the log of K is going to equal, and I suppose we can keep that in parentheses for good measure, N times standard cell potential over 0.0591. So as we look at the work that we have here, we've got a lot of the numbers that we're going to need to get going on calculating our equilibrium constant. And so N, as I had circled previously, that's the number of moles of electrons that are going to be transferred, which ends up being 2. Standard cell potential we calculated as 0.90 volts, and we've got our 0.0591 as our constant within the equation. So as we look at this, log of K is going to end up being about 30.46, we'll call it. So at this point now we just need to do a little bit of algebra to get to our answer. When it comes to getting rid of a log, it means we're going to raise both sides. We're going to take basically 10^2 on both sides, so meaning 10 to the log of K and then 10 to the 30.46. It's going to end up being a pretty big number. We'll see if the calculator can handle it, though I am not holding my breath on that one. But hey, looks like it can, and so the K value ends up being 2.88 times 10 to the 30th. So a couple things to keep in mind here when you're looking at your results or trying to figure some things out. As the standard cell potential gets bigger, the K value is also going to get bigger, because basically what we're seeing here is as the standard cell potential gets bigger, that's the push on the electrons through the system. And so as this cell potential or electromotive force measure gets bigger, there's more push on the electrons through the system, and so that also means that the system is more likely to end up towards the product side, because it's able to get more of its electrons to turn into the resulting solid and ion through the transfer of the electrons. So in other words, manganese is going to be able to give up a lot of its electrons that are in turn taken up by cobalt, and so the ratio between reactants and products gets further and further apart. We get more and more products and less reactants. When you end up having smaller cell potential values, things that are closer to like 0.2 or 0.1 or 0.3, you're going to have K values that are a little bit smaller. This is a pretty big K value, meaning that there's a rather large difference between the products and reactants. You're going to need a pretty small cell potential value in order to have K values that are close to 1, especially because oftentimes number of electrons transferred are going to be 2. We've got this 0.0591, which automatically is starting to turn this into a value of somewhere around 30 automatically, and so really it comes down to the ability of the cell potential to temper what the result is in terms of this number. So hope that helps. Again, calculation should be pretty straightforward. I mean, a lot of the skills you're going to be using are things that show up elsewhere, determining the number of moles of electrons and figuring out the standard cell potential. And then after that, it's just a matter of remembering how to get rid of a log. So hope this helps. Good luck putting it to use in your problems.